sum of an converges, then the limit as n goes to infinity of a sub n has to equal 0. This is a really simple property. Let me call this, let's call this the test for divergence. It's a simple property. It's not saying a whole lot. And as I said, we're going to be testing these series if they converge or diverge. And this is usually going to be the very first thing you do. It's kind of like how I was saying with integrals, just quickly check in your head, can I do U sub? Well, here, if I give you a series, you're going to quickly check in your head the test for divergence. But what makes this, I think, a little confusing for people is logically, how do I apply this? So, as an example, let me give you two kind of competing examples here. Let's take our sum 1 over 2 to the n. Notice here, I'm not telling you if it starts at 0 or 1 or 5 or whatever, because it doesn't matter. I'm not asking what it converges to. I'm just asking, does this converge to anything finite whatsoever? And if I change where I start my sum, it's just going to change it by a finite value. So that's not important here. So in this case, as we saw, this converged. In fact, when I let it start at 1, this actually converged to 1. And so what does my theorem say? If my theorem converges, if my sum converges, then the sequence also had to go to 0, the sequence of the things I'm adding up. And it is true that 1 over 2 to the n goes to 0 as n goes to infinity. So to be really clear here, on the one side I've got a sum converging, on the other side I have a sequence converging. But this is the thing that everyone screws up. The reverse is not true. It is not true that if the limit of an is 0, that if you add all those numbers up, the whole thing is going to converge. And the classic counterexample is the harmonic series. So, but for the harmonic series, 1 over n, as n goes to infinity, that certainly goes to 0. Yet if you add those numbers up, it diverges. So be super, super careful. So the test for divergence is exactly that. It will tell you if your series diverges, but it can never, ever conclude that a series converges. So if I give you some series like, oh, I don't know, sum of 1 over n plus 2, well, 1 over 2 plus n, that definitely goes to 0 as n goes to infinity. All that means is my test is inconclusive. It could potentially converge, but it still could diverge. And so what you actually would have to do at this point is some other tests. And we'll talk about that soon. Plenty of other tests that will help here. So conclusion. Could converge or diverge. In other words, there is no conclusion here. On the other hand, what if I ask you the sum n squared plus 2n plus 1 over 7n squared minus n plus 99? Okay, kind of rule of thumb, if your professor gives you something complicated looking that's absurdly complicated, then there must be an easy solution here. What's the easy solution here? Well, ignore the summation. What's the limit of that as n goes to infinity? You get 1 over 7, that's not 0. This has to diverge. Don't even need to think about it. Any questions? Yes.
So whenever the function converges, that means the summation would diverge?
if the function does not converge to 0,
Yeah.
then the sum can't converge. So it's like convergence of your ANs to 0 is a basic requirement for the series to possibly converge. If it does converge to 0, then you can do some other tests and decide if it's going to converge or not. So really the thing you're looking for is, does it go to something that's not 0? And if that's the case, then you know that it will diverge. Okay. Let's get started in the next section since we have a bit of time left. This is 11.3, and this is the integral test. Okay, so in the previous section, one thing we looked at again was the geometric series. Which would be something of the form, say, 1 over let's say 1 over 2 here. Well, now I'm going to look at sum of 1 over n squared. Looks very similar. It is not similar at all. Okay. So what I'm going to do is compare with the function 1 over x squared. So I'm going to compare this to something we know from calculus, and we're going to do an integral, as you can guess. And not only that, instead of, so let me write n equals 1 to infinity here, it won't matter in this case. What can I do with a continuous function? Well, I can integrate. And actually, the connection there is pretty, not straightforward, but it's kind of clear because integrals were defined using infinite sums in the first place. They were defined with these Riemann sums. So let me draw you a picture. Big picture. One over x squared. Something like that. 1, 2, 3, 4. And I'm going to draw under this curve a Riemann sum where my delta x is 1. So all my rectangles are going to be with 1. And like so, we're going to hit 1 over x squared at these points. And I can just look at the area here. Okay, so what is the area? The area of the rectangles that I have here. By the way, if you pay close enough attention, you'll realize I'm kind of cheating us here. That first rectangle shouldn't be there. It's not actually part of the Riemann sum from 1 to infinity. But it's not going to change my final answer here. My final answer is whether or not this converges to infinity or to a finite value, and one rectangle won't change that. So that's still open. So what's the area here? Well, this height here, which actually should be the same as the width, is 1. I've got 1 over 1 squared. That's my first one. And then times your delta x, but that's just 1. My next area will be, well, it has a height of 1/2 squared. Squared. 1 over 4 squared. And all these are multiplied by delta x, which is again just 1. And what do you have here? You have exactly the series we started out with. This is the sum. That equals 1 to infinity of 1 over n squared. So I can kind of use an integral to naturally come up with the series. And I'll just make a comparison in terms of area. I know that this area, this red area here, is bounded below the area of this 1/x squared curve. And I also know from what we did in 7.8, whichever section this was, that this converged. This actually converged to like 1, right? So this area is between 0 and 1. It's going to also converge. So by comparing with an integral that looks a lot like my series, I can decide in this kind of manner if it's going to converge or not. Does that make sense? I can write this as an actual rule so we can be more methodical about it next time, apparently. So, any questions? Okay.